The word mechanics in the name of quantum mechanics means the branch of physics concerned with motion, and motion has to be changed with time. And a speciality of quantum mechanics is that you can have a change of time in the sense that every particle is a probability wave, and the wave can move with a velocity. And now in this lecture I have included a definition of wave, which is, when I say one wave means plane wave, that is a definition which you can write in any exam. That is one topic of this course. And then is the next definition, which is in this lecture, is definition of what is called phase velocity. That means the velocity of this wave. And then its expression, that's the third topic. And then is the news, that this velocity is there, mathematically it is there, but its effects are not visible. Effects are not visible, and in that sense this velocity is not measurable, and that is not motion. So that completes one part of that. That's in lecture. And what else is in lecture is that measurable velocity is the velocity of these effects, or means the wave packet, means wave packet moves. There is a packet and there is a peak. When peak moves, it's called, because many waves combine to make a peak, so combine means it's a wave packet or it's a group. So group velocity, definition of velocity and expression of group velocity is included in the lecture. And for derivation, I am using a new method which is quick. It takes some effort to understand it, but once learned, it's quick. In one line, it gives a this expression, which others take quite much more time. So that's outline, and then go to the actual content. And that, as promised, the first I introduce you to definitions which you can write. The published definition which you can write in any exam. The first definition you need writing is a plane wave. When I say wave, I meant plane wave. So plane wave is a wave which has a fixed wavelength. Wavelength is from, say, crest to crest. This crest to this crest. This is a wavelength. And here you extend wave here, whatever it is, the wavelength does not change. That's a definite wavelength. That's one condition. And with time, vibrations per unit time, per unit second, number of vibrations, frequency, that also does not change with time. You remain moving it. You remain seeing the motion, and whatever time you spend on it, that per unit time vibration number does not change. So the two conditions satisfied, the wave is called plane wave. Now the formula used in quantum mechanics of plane wave is e power iota kx minus omega t. What a condition is, I said, wavelength, that's included is here. K, that's the 2 pi multiplied with reciprocal of wavelength, and that's here. And omega is 2 pi multiplied with the frequency, what I say, vibration per second. So these appear in this expression which is used for plane wave in quantum mechanics. Now if you have to see it in the graph, you have to take it, you have to get rid of iota, because iota is a minus 1 under root. You cannot make graph of it. To make a graph, you have to take a real part, which is a cos. And now you can use any machine to make a graph. And if you say that t is time, you just give the command that t is time, then you will see time motion. But that's mathematically calculated. And now when you have graph is calculated on the graph, you can see this crest. Crest is this angle is called phase. At crest, the phase, you may say the phase is 0 here, and here is 90. This 90 degree, or any phase. When phase moves with the velocity, or you can say crest moves with velocity, that's the definition of phase velocity. So that's the definition. Phase moves with phase velocity. And if you think it's a repetition, you can say crest moves with the phase velocity, or you can say shape moves with phase velocity. And if then should be sufficient for any exam. Now the Next topic is what is the formula for phase velocity, and the answer is the phase velocity is distance, calculated distance is wavelength per unit time. Per unit time is 1 over time is frequency. So distance per unit time, that's expression required. Traditional is that you multiply with 2 pi and divide by 2 pi, and this is you call omega angular frequency, and then you take lambda in reciprocal, that becomes wave number. So more traditional way of writing is omega over k, angular frequency divided by wave number. Now, so far I have not talked about is quantum mechanical effects. So motion was there, but I did not tell you is the motion is visible or not. For visible means effects should be visible, and effects means probability density, maybe the first effect I have told you in quantum mechanics, and that is wave function. You had a wave function that multiply with complex conjugate. When you multiply complex conjugate, exponentials cancel and you have a constant. A constant doesn't move. Think of that. Now, is the wave moving or not? In that sense, it is not moving. In the course, later there is a sense which is called probability current. For a plane wave, probability current is can be non-zero, and in that sense it would be considered as moving. But in the sense conveyed in this lecture, plane wave is not moving. And since it is not moving, so there is no physical condition on it. It can be greater than speed of light, but that's no clash with relativity. There is no visible clash with relativity. You can't measure anything which is it's below means it's not actually written. The phase velocity can be greater than speed of light is a thing. If you ask me in a comment, I can tell you just 2-3 line derivation is there. That phase velocity can be greater than speed of light for an ordinary particle. Okay, now I'm getting ready for the next slide, and for the next slide, it's for the connection of this slide and the next slide. I talk about an alternative way of this slide result, and this alternative way is you think that rather than multiplying with the complex conjugate, which is not if you want to concentrate on this graph, there you don't see multiply with complex conjugate. On the graph, what you can see is an envelope. Try to learn this word envelope. They move on an envelope. Okay, if it's a down both, and crest or trough both move in envelope, which is up or down envelope. The envelope is constant. Maybe for you there's two independent things, but the result is same at least. So try to remember that result. So now next we have to tell you what is the physical velocity, measurable. And for that I pointed out the word envelope. Now here I point out again what is envelope. That is, a quantum particle has to be a localized wave, since its probability has to be in a limited region, so that the total remains 100%. It can be finite. So if it is localized, that means its envelope has to have a peak, and then it has to become zero. Now if envelope moves, and in the previous slide envelope did not move, but here is if an envelope moving, if it is envelope is moving, then envelope velocity is called, because envelope is produced by a group of waves or packet of waves, so the envelope velocity is group velocity. Next I show you all three together. This is the third. This is envelope, means this is envelope. This is a group, many waves combine to make this, and then envelope or group velocity is this. This is that. It is moving forward, and now coming backward. It's forward, it moves backward. And now inside the envelope you have many plane waves. If you pick up one of the plane wave, then it's the phase of that, or maybe crest, trough here almost, of that moves with the velocity which is velocity of plane wave, and that is velocity of phase of plane wave, you can say, and that is the phase velocity. So I have shown all these together in a graph. So next job is to, if you want to write down the definition, which you can write in an exam, the definition of group velocity is the following. The group velocity is the velocity of the group of waves. And the alternative could be group making the wave, or velocity of the wave packet, or velocity of the envelope. You can choose, they all mean the same. Another way of saying it, it's the velocity of the peak. And the next in calculation, we have to concentrate on that thing. We have to know where the peak is. And you remember this peak, if the peak moves, we know that chances of detection move, and that's a visible, that's a measurable. And that measurable thing, velocity of peak, that cannot be greater than speed of light. So if relativity condition is on measurable velocity, which is that velocity, your chances of detection will increase. So next is the remaining part of the lecture is more mathematical, in that you have to see mathematical expression, formula of this wave packet, and where you have to recognize mathematically where is its peak. So for that I start with now in mathematical language. So far in qualitative language I have been saying that a wave packet is composed of many waves. So many means some, and some means this is a continuous sum, it's integral. That's the first mathematical lesson. So many plane waves. So plane wave is that's the next translated to mathematics. Another thing, that the weightage of different waves can be different. The weightage factor is phi k. So all my spoken words have been translated into mathematics, and the net result is a wave packet. Result of this packet means sum is a group. The group is this integral. Sum is that. Now we have to do mathematics on that. When is that maximum? Because that's the envelope. So for that I am using what I announced to be a new technique. This new technique is actually I have learned from an MIT lecture by string theory physicist or expert Zubich. So Zubich in his MIT lecture mentions a method which is, he mentions it, method is of mathematics. So now I explain what the method is. You know, the mathematically task here we have to recognize value of x and t where this whole integral is maximum. So inside integral you have a product. So the two things you have to concentrate on that are the following. One thing you have to remember is that the integral is area under the curve. And this area can be algebraic area, that can be positive, that can be negative, and net can cancel. So that's one lesson, that integral is area, algebraic area. The second lesson is this color scheme, try to understand. First we have to multiply. So multiply this, this is a purple, this is a plane wave. And then weightage factor is that, different k, different waves have different weightage, that's a blue. The result of product is shown is in black. And here the net result of integration is also in black symbol. And you have to say this where this black is maximum, that black is integral. Integral is area under the curve, area integral is maximum. It's a simple, you don't need to pay attention where is maximum, minimum, just say where it is 0, non-zero. 0 is minimum, okay. How is the minimum? And the answer is the following, is that here this purple is has positive negative. So this product also has positive negative. So the net area cancels, positive, negative, net 0. Here is 0, here is 0. But here the phase, this is the phase, is stationary, is not moving with k. You change k, it does not change. So there is no positive negative, only positive. So that means there is no cancellation here, where phase is almost stationary. So here is non-zero, and non-zero is maximum out of all possible. So that's a technique which is called stationary phase. So now we apply to it in a mathematical. Now I don't, in the next I don't show this graph. Try to remember this mathematics. And now we have to do calculus of that. And calculus, first thing is when you say stationary, what do you mean? Now stationary, you try to remember from here. Next is in the next slide I have only mathematics. So, but if you prefer graph, then try to remember from here. Stationary means it does not change with k. If you change k, it doesn't change. Now calculus says rate of change is derivative. So if it does not change with k, it means its rate of change with respect to k is 0, and the derivative with respect to k is 0. So that's all I can take you shape, and now I have to take this derivative equal to 0 mathematics and use it. No longer dependent on shape. And that is, I have written the question, where is the phase is stationary, and I spoken the answer. Do you remember what I said? I said stationary means is what? Try to recall. And it will be your check whether your answer agrees with what you have thought. Anyway, the check is there. What I said was that it does not phase, does not change with k. Does not change means its rate of change is 0. Now phase is angle, which is e power iota or inside cos angle, and that's kx minus omega t. It doesn't change means derivative with respect to k is 0. It's a simple mathematics. First term, k with respect to k is 1, is x. Now it's d omega over dk is here, t is outside. You rearrange it, you say x is equal to that. And can you see this is something familiar? X is equal to t. That is familiar from classical mechanics. If something moves, then I mean the most common is x. S is equal to vt, where x is distance is along x-axis, so it's x, and v is a group velocity, the speed of group, so it's a vg, and t is t. And you compare these two, that gives you the expression for group velocity in just one line, 2-3 lines. That's it, simple. Main thing was stationary phase technique. Once learned, you have just 1, 2, 3 line, whatever you say, call it. It's simple, one step in a way. So that's mathematics, that's a quantum mechanics. Now, because we have seen something similar to classical mechanics, and now another thing I can do in this course is that the claim has always been there in quantum mechanics, that in daily life quantum mechanics agrees with what you see with the classical mechanics. And here is the first instance of it, and that is if the peak moves, then peak moves, the chances of detection move, and you can say if the chance of detection maximum, you can say if your detector is your eye, then chances of detection maximum gets translated into is that you have most chance of seeing the thing. So where visible position changes, you can say particle changes or particle moves. So the peak velocity becomes particle velocity. So the expression which was there, which to you it looked like a mathematical, now you can have a physical meaning of it, familiar physical meaning, and that means it's velocity of particle. And this now again is a calculation which if you ask, I can derive for you, but your derivation is not needed, so I have not included definition here, that this is group velocity, velocity of chances, velocity of particle. That is what you see in daily life. So if in daily life you see a particle is moving, then quantum mechanics is not a contradiction to quantum mechanics. This is according to quantum mechanics. The only thing is it's a complicated, so people do not use quantum mechanics here and they prefer classical mechanics. But if you use quantum mechanics, that would tell you about this ordinary ball, and that would tell you that it's a wave function square. This means chances of detection, the chances of seeing it, they move with time. You say particle move with time, but there are two ways of saying the same thing. Quantum mechanical way is that chances of seeing change with time, and chances are wave function square, peak of wave function square. So that's all the announced aims have been achieved. Next I have only a verification, and then I finish. So and do verification of what? And the answer is that once I take you back and then forward. The back is here. In this derivation, we need not know what is phi k. For whatever is phi k, our calculation was valid. I'm bringing back. Now that's a general theorem. Whatever is phi k so far. Now I take you a situation where the phi k is known and we do actual calculation, and then this result gets verified. And what I'm saying is the following: phi k is given in that you do this integration, and here you don't need calculating area under the curve. You can do calculus, symbolic calculus, no area, don't depend upon area, do calculus, and the result is I've shown in some previous lectures. That is but you need not go to that previous lecture. It's just calculus, and it's so simple to at least understand. The result is that e power minus x square a square. And where is the maximum? A maximum is a minus, is the denominator. So maximum is when the denominator is minimum. That means x square is minimum, then x is equal to 0. So that is by actual calculation. Now I announce that that's a verification of what we learned in this lecture. New thing. That's not new thing. The new thing is lecture we said that the peak is obtained where the phase is maximum. Now the phase is kx minus omega t. In this calculation, kx minus omega t was kx. So you don't have to take derivative of kx minus omega t, you have to take derivative of kx. With respect to k, that becomes x. Station means derivative is equal to 0. And that means x is equal to 0. And that's a verification of what we did by actual phi k in this particular example. So this example result agrees with general result. So that's all I have to say. And now I do conclusion and then I finish. So what we have learned in this lecture is that a plane wave, so we learned definition of plane wave, we learned definition of phase velocity, and then we learned expression of phase velocity. And I told you that in the sense in which it is not moving. That's the first thing we did in this lecture. And the second is that I picked on that thing, the previous thing told that a physical particle is a wave packet. I gave another name to the packet which is called group, and velocity of packet means velocity of group. It's called group velocity, and its definition was taught to you, and then its derivation, its formula derivation was taught to you. And then it told you a connection with classical mechanics was conveyed, that if you say that where the peak is the chances of detection of maximum, if you like to say that at that position is the particle, that means the peak velocity is the particle velocity, same expression there, and that is a measurable thing, and that has to be less than speed of light. So that's all in this lecture. Hope to see you in the next lecture.